Welcome to the walkthrough to the exercises. So the first task was, how many optimization steps do you really need to find the minimum of the following function from the starting point x is 4 using Newton's method without step scaling? So the shortcut to this would be to understand that Newton's method fits the gradient, the functional value, and the Hessian of some function, meaning that the placing into the minimum of that fit is exact for any quadratic function. So without writing any code, you'd know that the answer to that question must be 1. But let's have a look at the source answer to this. So there is no Newton's method no pure Newton's method in SciPy, since the method is fairly inefficient, but has been the blueprint for any kind of more advanced algorithm. So let's write this optimization function on our own. I'll start by writing the function Newton minimize, which shall take 4 arguments. The first one we need is a starting value, because we need to have the initial conditions of x is 4 reflected in this. And then we require something that we can call, so a function, we require the gradient and the Hessian, because this is all ingredients that Newton uses. Okay, so we start by defining some variable that takes the current value, and we set it to the starting value because that's where we start. And now we have the for loop because it's an iterative approach. So we write for, say, I in range, or let's maybe call this a little bit better, for step in range 10. Just to give it as an idea, we print where we are. So we can say step is the step variable, and then we can say current value is current value, so that's our minimum position that we're looking for. Now, the Newton's method has one distinct update step, and we have looked at that in the lecture, so the slides contain the equation. And let's write a variable called update step, and it's minus the gradient divided by the Hessian. So we say minus gradient of that position where we currently are, so of current value, divided by the Hessian of current value. So now we have our update step. The minus is important because gradient would be the direction of steepest increase, and we want to go downhill. And now we just say current value is extended by the update step. So the function is done. Now we need to have the function that we want to optimize as code. We need the gradient and we need the Hessian. So let's write function of some value is, well, x minus 2 squared plus 4. That's exactly the equation that we have over here. Now we can say the gradient of something is exactly 2 times x minus 2. And of course the Hessian, we can also define that, which is easily identified as 2. So far, no surprise. And now we can call our function. So we can say Newton minimize. The first one was the starting value, that's x is 4 over here. The second argument is something that gives us the function value itself, so that's function. And then we need something that takes the gradient, and we need something that takes the Hessian. Now if I run this in the cloud, then soon we get our answer, which shows that in step 0 we are in the position 4, but in step 1 we are already in the minimum, so at exactly 2, which, as you can see from the equation, is the minimum position. So it takes precisely 1 step to go into that minimum. Now let's have a look at task 2. In task 2, the question was, minimization is commonly needed for regression or curve fitting. Use the random data in the following code stub to perform a least squares fit with SciPy optimize least squares to a quadratic function. And we have this import here. We set the random numbers and we get x values and y values. So in all this, we now need first to import SciPy optimize. So I write import scipy.optimize as SCO as one of the shortcuts presented in the lecture. Now in the lecture we had this example with the linear function, and I will follow the same procedure for this quadratic function. So we say def quadratic of some solution set, let's call this x0, which needs to contain all the polynomial orders because it's curve fitting, so we fit the coefficients of quadratic function. So let's split this up. Let's use this shortcut here, which in Python means if x0 contains exactly 3 values, name the first one a, the second one b, the third one c. I think that looks a little bit more convenient. Now we return exactly the value of the polynomial, so that would be a times xs squared plus b times xs plus c minus ys, because we want to minimize the residuals, and the residuals are the difference between our fit and the true target values ys. So now we have a function that can tell us what is the residual of a given set of x0s. Now we can ask our least squares function in the same manner as we did this in the lecture slides. So we say quadratic as the function, and now we need to give some initial guess of our values, and if it works, why not? We could just give it all zeros. So this is the list of 3 zeros in NumPy. And the result is in .x, so if I just run this, we get the solution vector for the fit. So it's nearly 1 for A, it's nearly 0 for B, and it's nearly 0 for C. And this makes sense because we've seen that effectively this is just x squared plus something random, so the something random gives rise to these two values, their deviation from 0, and this value deviation from 1. And so if I just use the x array excess element 0, I get exactly the value for A, which is the leading order term that you're supposed to report. So if I run this, I get my answer for task 2. Now finally, task 3 is a little bit more involved. So the idea is that we want to compare the number of steps to minimize SciPy-Rosen with Newton's method using a skip scaling of 0.4. So this means the same concept as we had it initially here, where we had no step scaling. We do the same thing over here with the Hessian. And we have a starting point given. The question is, how many steps do we need to go below 10 to the minus 8? And fortuitously, we have already the derivative and the Hessian implemented, so we don't need to derive that. We can just directly use SciPy optimize for that. Okay, let's build this. So I write a new function, which I call the same as before. You can always override this, and now it's going to work with a two-dimensional case because we have our two-dimensional Hessian in here. So we need some starting value. Again, we need a function, we need a gradient, and we need a Hessian. And the concept is the same as before. We write current value is equal to the starting value that we have initialized, which is going to be the minus 3, 2 that we have in the original exercise. Now, since I roughly know how many steps this is, I'm going to write this a little bit differently. So say for the step number in the first 100 steps, we want to calculate the gradient norm, because that's what we have here as a stopping criterion for our optimization. And the gradient norm, there's many different ways how you could write that, but one that I think is most instructive would be to use the linear algebra function from NumPy. So numpy linalg norm of some vector, and the vector would be just the gradient function at our current value. Now we have the gradient norm in the argument over here in this variable. Now we can print this. So we can say print step to be step, and let's say gradient shall be whatever is in gradient norm. But if the gradient is below that criterion, then we would like to stop. So we write if the gradient norm is smaller than 10 to the minus 8, then we would like to break the for loop. So this means exit the for loop whenever this is relevant. So this criterion is reached. Now, after we have calculated this gradient norm, it's the update step that we need to do. It's the same thing as for the one-dimensional case, now with the difference that we use a scaling function, the 0.4, because we're scaling our steps. So we say numpy dot of the inverse of the Hessian. So because we divide by the Hessian and matrix logic, that's the inverse. So we calculate the inverse, again, linalg dot inv for inverse matrix, and we take the Hessian of the current value. So this means first calculate the Hessian, then calculate the inverse thereof, and then multiply this with the current gradient at where we are. So from current value. This gives us the proper update step. You can, since this is always just 2D, if you don't want to use the linear algebra functions, at least for this case, you can write this manually by accessing the individual array of elements, since the inverse of a 2x2 matrix is readily defined. So now we can say current value plus equal update step, and this way we now have our new estimate of the next step. So I can run this by saying Newton minimize, and the first argument is the position where we start, so that's -3, 2. The next one is the function that we'd like to minimize. Then we need the derivative thereof, and we finally need the Hessian of that function. So with this, what we have is the individual steps of the optimization, and what we see is that in step 90s, so after 90 steps, now I've reached our desired threshold.